Free fall, air resistance, and terminal velocity. True or false? The speed of an object in the air will continue to increase without limit until it strikes the ground. Kind of true, kind of false. But the fact that it says in the air, okay, this is a tricky part. So as it increases, as the speed increases, their air resistance will increase and it'll eventually hit what's called terminal velocity. So I'm going to make a decision here and say that this is false. Because eventually, as it speeds up, the air will slow it down. And so just some vocabulary out of the way. Terminal velocity is that velocity you hit where all the forces are balanced, where the air force pushing up balances with gravity pulling down. Okay. Now a tennis ball and a solid steel ball, a tennis ball and a solid steel ball are the same shape and dropped at the same time. In the absence of air resistance, what is the force acting on both of them? The normal force, the force of gravity. There aren't any forces acting on them. Oh, well, certainly gravity, because you're on Earth. Normal force is that force, remember, when you're on a surface, but this is dropped in the air. And so I'm going to say force of gravity. Tennis ball and solid steel ball are the same size, dropped at the same time. In the absence of air resistance, which ball has a greater acceleration? Well, the acceleration does not depend on the ball. The acceleration depends on the planet that they're on. And if they're on the same planet, they have the same acceleration. Nonsense. As the ball falls from a high-flying stationary helicopter, and there is air resistance, good to know, Bronco's velocity increases and his acceleration as he falls from a high-flying stationary helicopter. His acceleration is going to remain the same because, again, acceleration does not depend on anything else except the planet that you're on. And the planet has not changed, so acceleration remains the same. How does air resistance change as Bronco falls from the helicopter? All right, well, faster, I'm going to assume Bronco is a guy, person that came to mind. The faster he falls, the more air resistance. And so, the longer he falls, the faster he falls, the more air resistance acts on him. What causes the air resistance to change as Bronco falls from the helicopter? Hint, it is in your textbook. Well, there are two things that change that affect air resistance. Those two things are the shape and speed. So if Bronco is changing his shape, let's say he was a ball, or he was like diving off of a diving board, really tiny, and then he went out really large, like a starfish, well, then his shape might change and his drag may change. But certainly, as he's falling, like I said in the previous question, his speed is increasing, and therefore his air resistance is going to increase. What is the air resistance and acceleration after Bronco exits a high-flying stationary helicopter? So as he immediately leaves, we can say that he's practically not moving. And so if he's not moving, right, the speed is practically zero. So his air resistance is practically zero. It's like he's just kind of falling. He's just standing on the side of the road. If you're not moving, well, you're not feeling much air resistance. And acceleration, if you remember this one fact, you've gotten 3 or 4 of these questions correct. The acceleration depends only on the planet that you're on. It is equal to g. Always, everywhere. Can't convince me otherwise. Okay. So now we have to describe, as he's falling through the air, what is happening. Well, acceleration, again, only depends on the planet that you're on. So we're going to say this is 10 meters per second squared. And I'm just going to kind of copy paste this down. Well, instead of copy pasting, because that's kind of tedious, I'm going to use those quote marks to say same as above, right? So I'm just going to say same, 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 same. Acceleration due to gravity isn't going to change unless you teleport to another planet. The air resistance, we said, is practically zero. These are in newtons because it's a force. After he's fallen a short while, I'm just going to say it's small. It's not zero anymore, maybe 1 or 2. Just before he reaches terminal velocity. So let's say it's 9. Because again, I'm going to forget about c for a second, because terminal velocity means that your air resistance has matched your acceleration. That is what terminal velocity means. So I'm going to say this is 10 newtons. And so just before that, maybe it's 9, 9.5, whatever you want to say, just barely under 10. Immediately after he releases his parachute, and now I'm going to say, ooh, it is like 1,000. It's a huge number. Maybe not 1,000. I'll call it 100. I don't know. But way more than the acceleration due to gravity. So it's shooting upward. A short while after he releases his parachute. Well, after he reaches his parachute, it's going to be slightly less. I'm going to say, all right, 99. Because the most air resistance is when you're moving the fastest and when you have the biggest shape. So that is immediately when he releases his parachute. Then after that, he starts to slow down. So a little while later, the speed decreases a bit. And so, the air resistance is just that much smaller. And then a long time after he reaches his parachute, eventually it's going to balance out. Again, we're going to hit 10 newtons again to match the acceleration. It's not going to be going speeding up or slowing down for the rest of his trip. Okay, draw the forces acting on the skydiver for situations A, C, and D. I guess we skipped B, didn't we? So if we say immediately after he exits the helicopter, he has nothing pulling him up because he's not going fast enough for air resistance to really impact him. But he does have this force going down. And we don't know his mass, we don't know his kilograms, so we don't actually know his weight. We know that it is accelerating downwards because of gravity. And I'm going to try to keep this arrow consistent. In the next one, we have just before he reaches terminal velocity. So I'm going to say, all right, can I copy paste that? Oh, yes. So we do have that. And what I'm going to do is I'm going to match it. I'm going to flip the arrowheads and say, all right, this would be if they're equal. Well, just before it reaches terminal velocity, it is just barely not equal. All right, so he's still coming down faster. He's still accelerating downward, speeding up, but just barely, right? So I can't really say newtons. That's a mistake. But we could say it's just less than, I'm going to get rid of this. Just before it reaches terminal velocity, the acceleration downward, the force downward is just barely larger than the force upward. And once he reaches terminal velocity, I have these two arrows here. Certainly the force of gravity has not changed. That arrow is still the same. And now at terminal velocity, again, I don't really know the numbers here because I would need to know his mass or his weight in order to answer that. But what I do know is that they are equal and opposite. They are balanced. So immediately after he releases his parachute, he has the same force of gravity acting on him going down. I even borrowed the same exact arrow, so it's the same gravity. Gravity has not changed. But now if I were to place this here, he has an enormous amount of air resistance. I mean, I'm going to make this arrow literally as long as I could possibly make it. Now I'm going to use these arrows as kind of like a reference for the next ones. So I'm going to copy it. The next one is very similar. A short while after he releases his parachute, Well, what's going to happen? Gravity does not change ever and always unless he teleports. So this is going to be just a shy bit smaller because his speed is decreased, and so therefore his air resistance is decreased. And then a long time after, he will eventually hit terminal velocity again. And I'm going to make sure these arrows are matching sizes, and hopefully it'll tell me when. No, it doesn't. So I'm going to copy paste the same length arrow and just switch the arrow directions. And now these are equal and opposite. Terminal velocity again, but now it's much slower because he's slowed down. He had all that time with air resistance pulling him up and slowing him down. And that is the review.